Okay, good morning, everyone, and thanks for coming out on this rainy, dreary Tuesday. It is our pleasure to have with us today Professor Alessandra Corsi, visiting from Texas Tech University. Alessandra is an expert in time domain and multi-messenger astrophysics. She is a fellow of the American Physical Society and the recipient of many different awards, just some of which recently include having received L'Oreal UNESCO Award for Women in Science, an NSF Career Award, and she was one of the recipients of the 2022 New Horizons Prize in Physics from the Breakthrough Foundation. She's going to be telling us today about multi-messenger observations of cosmic collisions and explosions. So please join me in welcoming Professor Corsi.
All right, thanks a lot. It's a great honor for me to be here, and thank you for the invitation. I hope to be just giving you an overview of the current research I'm working on and what are the future prospects that I think are exciting in the multi-messenger study of compact objects. So I will start introducing this topic very broadly. So we have here the mass spectrum of compact objects, from those that are in units of solar masses, close to the mass of our sun, to most that don't even fit in there, billion times the masses of our sun. And so we're looking at neutron stars down here and heavier black holes over here. And we are living in a really golden era of exploration of compact objects, because now we can study them with multi-messenger observations. So most of my research lies in this lower part of the mass spectrum, dealing with explosions and transients that seed the universe with neutron star or stellar mass black holes. There are several really interesting opportunities in multi-messenger astronomy going towards the higher mass of the black hole spectrum, and in trying to understand the fuzzy dividing line between stellar mass black hole and what we call intermediate mass black holes. I won't cover those here, but I thought I would put all this into context, and perhaps for those of you who are following the lunch later, we can discuss a little bit the most massive end. But thanks to gravitational wave observations today, we have a few examples of this low mass neutron star and black holes in binary systems. Certainly the most famous GW 170817 is the example of a merger of two neutron stars, from which we've seen gravitational waves in light at all wavelengths. And so I'll start from that example to discuss today what is most interesting from my perspective going forward. A couple of black hole neutron star candidates events, and then pairs of black holes that get into the realm of the gap between stellar mass black hole and intermediate mass black hole. And all of this, compact object study in multi-messenger astronomy can give us insight into stellar evolution, explosion, physics of ejecta, and up to the way of the highest massive black holes that impact the dynamics of galaxy mergers and accretion on more local scale with gas. So there's a whole lot of physics that we're trying to explore, and today I'm going to focus on a only tiny window of all this. Just to give you more of an idea of who I am, I'm an observational astronomer, and so I study these phenomena from an observational perspective. Mostly I like study core collapse, supernovae, and gamma ray bursts. So these are the link between the two, trying to search for the most relativistic explosions that seed our universe with neutron stars and black holes. And as gravitational waves now are allowing us to also study these explosion when they involve two neutron stars or a black hole and a neutron star, I'm also very excited about the multi-messenger aspect of these transients. I'm part of the LIGO scientific collaboration, and inside of LIGO, I spend half of my time playing with their data and trying to find new post-merger signals, trying to understand what happens after two neutron stars merge. But I am a heavy user of particularly the radio band of the electromagnetic spectrum when I like to study these transients. And so I'm going to be talking quite a bit about the very large array and the future, the next generation very large array. In order to identify these transients, I rely on optical surveys of the sky. So many of the things I'll be talking about involve the Zwicky transient facility. I'm a heavy user of Swift in X-rays. And then, as I said, I use LIGO data also for part of my research. If over the course of my talk, I hope to highlight what comes next, which is in this next row here. I'm very excited about Rubin soon starting to get data, but also I'm heavily involved in the defining the scientific objectives of the next generation of radio arrays and the next generation of gravitational wave detectors. So I'll be highlighting that and saying a few words about that. As I said, I won't have time to discuss LISA, but I find the prospects of multi-messenger observation of high mass black holes with LISA really interesting. So again, I'll leave that for the lunch. Okay, so this is mostly geared towards students or people who might not be in the field. Why do we want to talk about multi-messenger astronomy? That's basically joining two different messengers. In my case, I'm focusing on gravitational waves and light. And the reason for that is that when you're dealing with compact object mergers, such as the merger of two neutron stars, the gravitational waves can give you insight of what happens really close to that system as the two neutron stars dance around each other and eventually merge. But then using light, electromagnetic waves, you can study what happens after that smash up all around that site. And so it gives you more of an idea of how the matter that is ejected interacts with the surrounding and all of the astrophysics that is involved. And we give this for granted today, but when I started my PhD, Virgo was taking its very first data that weren't even considered scientific data, and it seemed like a really long shot to try to detect gravitational waves. So I'm really glad that we are in this new era. As an example of what is really exciting and what we hope to be doing more in the future, I'll bring up the GW170817 event. As probably all of you know, this was the smash up of two neutron stars on August 17 of 2017. And it was the first event detected by the LIGO and Virgo ground-based gravitational wave detectors in gravitational waves and light. So in this lower panel here, you probably can't read, but this is time from merger. So 0 is the time when these two neutron stars smash together. And then you're looking at their dance coming closer and closer in gravitational waves as they emit the signal. And this is a frequency versus time map. You can think about it as a music sheet. So it tells you where most of the power is in the gravitational wave emission as these two objects come closer and closer. So the frequencies are going up until the time of the merger. The upper plot is gamma ray counts versus time again. This is from Fermi, and it's showing a blip, a spike of gamma ray emission about 2 seconds after that gravitational wave smash up. So this was the first direct link between a merger of two neutron stars and a gamma ray burst. And gamma ray bursts we had known before are explosions that are related to the launch of the most relativistic jets we know in the universe. We already knew they were probably related to the different classes of progenitors, collapsing stars on the one end and merger of black holes and neutron stars on the other end. But this was the first direct proof that binary neutron star merger could give off a GRB. Now, the gravitational wave detectors, LIGO and Virgo, that saw this signal work pretty much like a pair of ears. So they localize stuff in the sky by timing. And so the positional uncertainty that they were able to localize this event in the sky, that dark gray area over there, seems small in that view of the celestial sphere there, but in reality it was 28 square degrees, so it contained many full moons. And so it was a real challenge to go find a signal that, however, we did expect in electromagnetic emission after that. The reason why this was a huge hunt, more or less, with every single telescope on the globe about finding the electromagnetic counterpart of this event is that we knew from ordinary gamma ray burst observations, those for which we don't know gravitational waves, that emission from radio all the way to X-rays should follow that gamma ray burst. And so the first accurate localization of the event was in the optical. This is the host galaxy of GW170817, about 20 days before explosion, and this is about 11 hours after, and you see that new dot of light. And as you've probably heard many times, there was an astonishing, really amazing discovery, I think triumph of theory, I would say, of the kilonova emission associated with the smash up. So this is an optical transients that in the various band of the electromagnetic spectrum evolves fairly quickly. So it's just a few days in the bluer part, and then perhaps 10 days in the redder part, or a little more than that. But it's associated with the R-process nucleosynthesis that happens in the neutron-rich debris that is formed after the two neutron stars smashed together. And that allowed for the very precise localization of this transient. So that's where my work came in. Most of my contribution was in the radio, and we had to wait 2 long weeks after this neutron star collision before anything was visible in the radio. What you're seeing down here is the host galaxy. That's the radio emission from that same galaxy there. That's an unrelated source. And you can see the counterpart of GW 17817 not there on September 1st and then appearing on September 7th. So we thought, this is really miserable. These 2 weeks were so long to wait. But then we realized that it was really actually a great result that that radio glow came delayed. And I'll explain in a moment why. I will highlight that this detection was only possible because of the very large arrays. So this awesome facility we have in the US, if you haven't visited the very large array, you really should. It has open houses, especially now that COVID's over. And this is an array of 27 dishes of 25 meters each. They work like a combined telescope where the resolution mimics that of a telescope this big, so the size of the array. And you can climb on the antennas if you've never been there. They let you go up. You really discover it's a parabola if, like me, you get stuck there and not able to come down, so you have to roll. But if you're slightly more athletic, I definitely recommend visiting. So this was the array that gave us the sensitivity to bring up a transit that was really, really kind of faint at the moment of detection. But the most surprising thing was that based on gamma ray burst observations, we were expecting a fading transient, so something that would be bright and then fade away over the course of days. So this 2 weeks delay was kind of puzzling. In addition to that, as we kept observing, this is the radio light curve at 3 gigahertz as a function of time. As you can see, over the first 100 days really of this event, what happened is the emission ramped up rather than decay as we would have expected. So we've learned afterwards that the reason for that is that we were, for the first time, observing a relativistic jet emitted by this smash-up of neutron star off axis, so from the side. So this is a cartoon representation of what you can imagine happened after the merger. The merger site would be over there. There's this kind of orangish debris, which is what powered the kilonova emission. And then associated to that, in the radio, what you see is the fastest part of your ejecta. You're seeing non-thermal emission. And so if there is a fast ejecta tail, say 30% the speed of light or more, you are preferentially probing that in radio from radio to X-rays. So what the radio shed light on together with X-rays was this existence of a relativistic jet emitted presumably along the rotation axis of the two objects perpendicular to their plane, but we were observing it off axis, so slightly tilted compared to that. So this was the very first time that we could appreciate what's in between that fast jet core and the rest of this lower debris, and it's indicated here as this jet wings. So it was the first time that we could probe what is the distribution of speed of the matter that is going faster in that ejecta. And we realized that in typical, usual gamma ray burst observations, where we typically sit aligned with this relativistic jet, we wouldn't be able to see this lower, moving ejecta after all, which contributed, in fact, to the emission at very early times. So to put it simply, if you just had a very fast core and you were observing it off axis, like in this situation, and there were no jet wings or distribution of speeds, you would have seen a curve, very rising very steeply to the peak and then decaying, while we saw something rising on a shallower profile, which were allowed us to determine, what is, on the side of those that jet. So it was what we call a structured jet, and was the first time that observationally it was possible to probe it. Now, I will point out that theories in gamma ray burst had, in fact, discussed many years earlier the possible structure of relativistic jets. observers kind of ignore it all the time because all we were able to see most of the time is GRBs aligned with jets. And so those are the ones that we typically detect in gamma rays. Eventually, the jet core does come into sight. The relativistic beaming as the relativistic ejecta slows down enables you to see radiation from the core, and that is when the curve peaks. And then you slowly see the curve fading away as the relativistic ejecta decelerates. So this color coding here kind of corresponds to the various parts of the ejecta that dominated the emission. The dark blue part is coming from the winds. When it peaks, you see the core. And then here you see the fading away, which I'll discuss a little more. Why is that interesting in just a couple of slides. So great. We did this with GW 17817, but it was 2017. And so what's next? And right now, LIGO and Virgo, well, LIGO is taking data. Virgo is supposed to be joining soon what we call the fourth observing run. And the thing that we would really like to do, I would say, over the next 5 years, is to go from one event like GW 17817, where we've paired gravitational waves and light at all wavelengths, from 1 to 10, really. 10 is good enough that we can at least start doing some statistics or start understanding better what the population or diversity of this events is. So here there's a bit of a cartoon representation of what you might expect. Over the mass spectrum that I highlighted at the beginning, you can expect neutron star systems or black hole neutron star systems. So from lighter to heavier systems in terms of total mass. And you can ask yourself, would they all look like GW 17817? We expect no, that there should be a variety of observational properties related to what they form after the merger, whether they can form a quasi-stable, so a temporarily stable neutron star or a stable neutron star for the lightest system, or promptly form a black hole for the heavier systems. Corresponding to that, so depending on what the output is of what we call the merger remnant, there should be a variety of different observational features out there. So something like GW 17817 is up here, where the merger happens. We've seen a kilonova with blue to red colors, and then a relativistic jet. And this presumably did form a neutron star, at least very briefly, that then collapsed to a black hole. But if you look, for example, at what could happen for lighter systems, you might ask yourself, well, if a stable neutron star is in fact formed after the merger, could there be the launch of a jet, question mark, of a relativistic jet like we've seen in GW 17817? And we would expect the kilonova to be brighter, perhaps cooler. In the other extreme case where you have prompt collapse to a black hole, perhaps we can see a bright relativistic jet as we see in ordinary gamma ray bursts. But what about the kilonova? Are we going to be able to detect it? Is it going to be too red, too dim, and so on? And so this is the type of questions that we hope to answer that I've highlighted here. What is the mass distribution of these objects, and what type of remnants can they produce? And how does these remnants and general properties of the system in terms of masses link or map to geometry, energy, and speed distribution of the ejecta? There's more to that: magnetic field amplification, ISM density, and so on, that you can probe with electromagnetic emissions. The nature of the merger remnant is also very interesting for placing potentially constraints on the equation of state of nuclear matter, and also in terms of prospect for future gravitational wave detectors. So I'll discuss a little bit about that in what comes next. Okay, so I promised that I would highlight a little bit what is going on at very late times in this radio emission from GW 17817. The reason why I'm bringing this up here is that we're writing another paper right now about what we're seeing at very late times in the radio. The reason for this is, if you notice, there had been some possibility, some claim about a potential rebritening in X-rays of this event at very late times. So we're talking about years after the event. We haven't seen any of such excess in the radio, and we're still monitoring, though the data point isn't published yet, is another upper limit that we're getting right here. But more broadly, I wanted to comment on what is the interest that this potential brightening at late times, why is it spurring so much interest? So the idea is, if you go back to my schematic view of what happened in this ejecta, is once the jet fades away, so its emission has faded from your view, you might imagine that the same dynamical ejecta, this orange ejecta here, that powered the kilonova might have had a faster tail. So something going at order 30% the speed of light, something like that would become visible in the radio once the jet fades, and it would do so at very late times. Whether this tail is detectable or exists at all is broadly linked to the equation of state of the remnant that forms there. In particular, you can have faster ejecta tails if the equation of state is softer, and so if you have core bounds during the merger, after the merger. So these curves here are just very simple analytical approximations of what you might expect in terms of late time rebritenings, depending on how much matter is coupled to fast speeds. And so these curves here go from faster ejecta basically to slower ejecta overall. A more detailed calculation have been presented in this paper that I'm quoting here by Radish et al., where you can see that depending on the neutron star equation of state, you can predict different profiles for the speed versus mass in the ejecta coupled to those speeds. And I'll just highlight two examples. So if you consider here a softer versus stiffer equation of state, so that red versus that yellow, then you can see that the red one, the softer one, predicts higher speeds or more mass coupled with faster ejecta. And so that would be the type of thing that you could constrain if you were to detect this late time radio emission. As I said, we're not having a detection yet, but we keep monitoring this event. And so I hope that with more events like GW 17817, eventually we can catch this fading tail. So I said that what's really needed is to have more of these events. So going from 1 to 10 over the 5 years would be a really nice result. And I wanted to discuss the prospects of that. So LIGO is taking data during its 4th observing run right now. And Virgo should join soon. There's going to be some more official statement, I think, around the end of the month of when it would be able to join the LIGO run. And then data exchange and plans for joining are also going on with CAGRA. But so far, the estimates that we've got is if you focus on those binary neutron stars that might be localized to 100 square degrees, and I say 100 square degrees because it's huge, but it's tractable with large field of view telescopes. So it's reasonable to say if you have 100 square degrees, there's going to be a decent hunt for transients in there for kilonova. The expectations for 04 are, of course, have large errors, but are in between 1 or 10 per year. In the forthcoming runs, so this is 2028, 2029, the next observing runs where the LIGO and Virgo detector will be upgraded, the estimated rates are at least something like 10 per year. So I would say that even with these, large error bars over the next 10 years, so between the 04 and the end of 05, we have decent hopes that we should have at least 10 events localized to 100 square degrees, again, if everything goes according to plan. So we're working right now on a large VLA program to do exactly what we did with GW 17817. We haven't triggered yet because Virgo hasn't joined the 04 run yet, and so far the localization areas have been really big. But we are ready to cover the whole duration of 04, hunting for more of these radio transients. So in any case, it's pretty clear that going forward, at least, as I said, for the next 5 years or so, the game is going to be to being able to localize transients in large localization areas, so order of 100 square degrees. So I think in this respect, Rubin is a very exciting prospect. Right now we have ZTF. This is showing their field of view to scale. So this is 47 square degrees for the Zwicky transient facility, and Rubin is about 10 square degrees. And we can hope of mapping kilonova ejecta to progenitors over these events that are better localized, with the aim of understanding better our process nucleosynthesis and then the yields of the various progenitors. On the right-hand side plot, what I'm showing is, in terms, if you compare the observational facilities, like a collection of those with larger to smaller field of view that we have right now that could go after the kilonova emission. This is a function of wavelength, and then the horizon redshift, so how far they can see This is from Chase et al. This is the LIGO horizon over here. And the diamonds that you see there are basically something like the GW170817 kilonova projected at that redshift and what Rubin could see. So Rubin is very promising, assuming there's going to be some time for TOOs. Up here, this one is Roman. It's very promising, except that the field of view is a lot smaller. So for the next, I would say 5 years, the combination of large field of view, about 10 square degrees, and sensitivity of Rubin is very promising, certainly for people like me that want to do the radio counterparts. And so we need accurate localizations because our field of view is rather small with the very large relay. So are there other ways? What if a kilonova isn't detectable? Are there other ways that you could find these things and localize them to the point where, for example, radio telescopes could point at them? So I did want to bring up this program that we have approved right now, which is thinking more about the gamma ray emission. That was the first signal that we've detected from GW170817. And so if you plot as a function of redshift, the energy, the high energy emission from gamma ray bursts that were presumably coming from compact binary coalescences that we knew before GW170817. This is the orange dots here. And you place GW170817 on this scale. What you see is that GW170817 was subenergetic compared to the gamma ray bursts we have known before. So the reason for that, or at least part of the reason for that, is that that event was observed off axis. And so it was actually slightly surprising that we were able to see gamma rays from it. Less, I think, if you think about a structured jet, so something which isn't a simple uniform cone, but has some wings. And so you have some energy reservoir when you're observing off axis. So you could ask yourself, well, could there be other events like that that are subenergetic in gamma rays that we could use, for example, something like the Swift bat to localize to Arc-minute precision and then go after them in the radio without having to use necessarily the kilonova ejecta. On the right-hand side, I'm showing a plot. This black curve with the error bars in gray is a very simple assumption that you can make taking the structured jet, so the energy as a function of viewing angle of the jet that we have studied for GW170817, and asking yourself, okay, so if I take a certain viewing angle from the axis of that jet, GW170817 sits here. It was about 20 square degrees, and that is the total energy in it. You could pump that energy up, and you would see basically a higher energy emission if you are more on axis. That's what this plot is showing you. So the question is, could there be events that in gamma rays are subthreshold right now because they're subenergetic, that something like Swift could observe in conjunction perhaps with subthreshold gravitational wave events, and those would be certainly events that are beyond 350 megaparsecs or so. So in this yellow area here is a type of analysis that you could do. So events like this, is they have the same GW170817 structure jet. You would see them as subthreshold in gravitational wave, but you could still detect them with something like Swift. The reason why I'm bringing this up is if some of you might be familiar with it, LIGO and Virgo are now releasing not just very significant detections like GW170817, but also subthreshold events. And so there's an effort going on with Swift to try to join the data streams and see if perhaps we could be missing a population of subthresholds event joint detections in gamma rays and gravitational waves. So we were exploring opportunities for new identifications of new transients in this way as well. Now, beyond the next 5 years, the question is, when is electromagnetic follow-up going to be made easy? We're certainly looking forward to that. So for this business to become easier, at least from the observational perspective, we really need better localizations from gravitational wave detectors. And you can achieve that with better sensitivity. So here's roughly a timeline of what the roadmap we hope will be in place for gravitational wave detection is over the next decade and beyond. So for the 2030 to 2035s, there's certainly concept that has been studied, most recently referred to as SHARP, which is basically take the current 4 kilometers long arm LIGO and Virgo detectors and push them to the best sensitivity you could ever achieve. And that would bring you to something like a 600 megaparsec range for neutron star mergers. Beyond that, you have to simply build longer detectors, so longer arm detectors. And a concept is being developed right now called Cosmic Explorer. You can think about this as super LIGO. So it has 10 times the length in arms of LIGO. So it would be something like 20 to 40 kilometers, depending on the configuration. We hope to have one 2 kilometers and one 40 kilometers arm. But broadly, they give you 10 times the sensitivity of LIGO and Virgo. Quick note, they're referred to as next generation sometimes, but sometimes in the literature, these future ground-based detectors are also referred to as XG, which I think stands for next generation, but it makes me think of the Starbucks extra grande size, which is appropriate. But the notation is being misleading. So it went from NG to XG, but that's the concepts we have in mind. And in Europe, there's the Einstein telescope one that is being developed right now. Discussions are going on into whether there can be some coordination between the US roadmap and that of Einstein telescope. The reason why I'm bringing this up is there was a recent call from the MPSAC of the NSF to bring forward this concept for what should be the next concept of gravitational wave detector. And there is a consortium that you can join if you're interested in the topics that Cosmic Explorer, the science that Cosmic Explorer could do, and it's open. So I'm putting that link there, especially for students, but really anyone interested. So what could Cosmic Explorer do? What can we hope for? Say, if we go to the 2035s, I think a good visual representation is here. So if we start from the very local universe and go at larger and larger distances, so GW 170817 was roughly 40 megaparsecs. So it was the closest short GRB ever observed. So kind of lucky. And the question is, if you simulate a population of binary neutron star mergers, they would be distributed as something like these yellow dots. And this is redshift 10, by the way, but for reference. And so what type of gravitational wave detector would enable you to catch that population? So going beyond the current horizon. So the Cosmic Explorer for the binary neutron star merger horizon is here, is this purple band. So you can see that you would be able to probe the bulk of this population, but even more importantly, the thing I like particularly is that you would be able to probe basically every binary neutron star merger out there, out to a redshift of Z2, which is the peak of star formation. And in practice, from my perspective, what that would mean is for every gamma ray burst that we see today in gamma rays up to Z2, that we don't detect gravitational waves for, and we have no way of mapping the progenitor into that relativistic jet, there could be a complete mapping at least up to the peak of star formation if you have something like these gigantic ground-based detectors. So you could answer questions of like, when is a jet launched, mapping one-to-one these events for the first time. The other thing that I really like, and this table is way too busy, I'm only gonna focus on a few of the metrics up here, but I've put the reference of the white paper that was submitted to the NSF and PSAC just this summer. Please go and look at it. The other thing that is really interesting is these binary neutron star mergers that will be detected at least up to redshift 2 will have localizations area that are as the best available today. And in fact, something like 100 of these binary neutron star mergers per year could be detected to less than 1 square degrees, which is amazing today, music for my ears, because in 1 square degrees, you go and point your radio telescope with a few tiles, and you don't need to depend on optical or gamma rays or anything. So you're starting to probe relativistic jets, regardless of whether you see them on other wavelengths. And radio, for the thing that it's able to probe up to low speed of say 30% the speed of light relative to other wavelengths, and you can catch it in spite of relativistic beaming, is extremely promising as a counterpart for off-axis events. So I'm very much looking forward to that. And then overall, the thing I think I should highlight is with the extreme sensitivity of these detectors in terms of neutron star physics, you can do two key things. Do GW170817 events nearby really well, with everyone going after the transient regardless of localization in other bands. And you can do the faraway stuff up to, say, star formation peak, mapping one by one progenitors to jets. There's much more physics there that I'm even involved in. And so that's why I invite you to look at this white paper if you're interested in working on the topic. You can ask yourself, okay, that's great. So these gravitational wave detectors are gonna be going to Z2, but can you detect their counterparts at Z2? Because many of these, like the Kilonova emission, is probably going to be too dim. Certainly, we are still going to be able to probe jets that are on axis, as I said, so mapping progenitors to GRBs. But I'm very interested in the question of what do we need in the radio specifically to go after this higher distance detections in gravitational waves as gravitational wave detectors hopefully improve. And so the other thing I wanted to bring to your attention is the next generation very large array. This is an array for a concept for a next generation radio array that has just received, if you haven't heard news, another $21 million grant for design, preliminary design. And so the roadmap for this array is similar, a little earlier, but on the same time scale overall, since these gravitational wave detectors and radio arrays last for a long time, of Cosmic Explorer and, in any case, improved sensitivity detectors. So we are right now in this 2024 where the antenna prototype is supposed to be delivered. And then right now we're working on what the transition era should be. So I told you about the VLA. The next generation very large array, you can think about it as a very large array with 10 times the antennas and 10 times the resolution. So rather than being in New Mexico, Socorro, where it is right now, it would spread across states in the US. And here's a better map. There's a secret. The reason why I put up this map is it's pretty much the only time you see Lubbock, Texas, where I live, on marked on a map. So there will be an antenna out there coming close to Texas, but you can see the distribution is spread really across states. And for those of you that are interested in radio observations, either for what constraints to set on your models or for the observational side itself, again, the sensitivity is going to be 10 times better than what we've seen with the VLA, 10 times the resolution. The frequency range will bridge from something like SCA to ALMA, basically. And it's going to be a more complex array than the VLA today to enable, dense core of antennas for low surface brightness. And as you can see, longer baseline antennas where the current very long baseline array sites are, with improved sensitivity to enable for order of 0.1 milliarc seconds resolution at the highest frequencies. So if this proceeds, then we're going to have, hopefully, as years go by, improved gravitational wave detector sensitivity, shown on the left-hand side plot, and improved radio sensitivity. So let me explain these plots quickly. So here we have frequency and gravitational wave emission and the noise of the detectors. It's the power spectral density of the noise. So the lower this curve, the better. And O4, LIGO 04, so current LIGO run is this black curve up here. The Cosmic Explorer detectors, the ones that I told you are usually referred to XG, don't particularly like that name, is this sensitivity down here. So you can see is a decent improvement. That the dashed line is the 20 kilometers and the 40 kilometers is down here. So with this improvement in sensitivity, you can ask how far can I be able to catch those radio transients? And so that's plotted on the right-hand side. This is days since explosions, and then the 2 to 3 gigahertz light curves based on the models we have right now of GW170817. This is subject to huge uncertainty because we haven't mapped the diversity of the events. But certainly we know that GW170817 compared to other gamma ray bursts was challenging to detect. It was rather dim in the radio. And so the curves in black, blue, red, and purple kind of follow the distance horizons of what you could do with various gravitational wave detectors. The dotted vested dash have different assumption of the density of the interstellar medium, so more optimistic assumptions on that and less optimistic assumptions. And the sensitivity limits of something like the Very Large Array and the next generation Very Large Array are indicated here in magenta. So you can see that what we can do right now today with the Very Large Array in 1 hour is only probing really the tip of the iceberg of these transients. If you had something like the next generation Very Large Array and a localization area of 1 square degree, which I told you Cosmic Explorer could do for several hundreds of events per year, then in 1 hour you could reach this level here. And if you had something like the next generation Very Large Array and the longest integration time we're spending today to find the tail of GW 170817, you would reach down there. So we would be exploring a much larger phase space of this type of explosions. Okay, so I want to shift gears a little bit for the next, say, 10 minutes and highlight something else that you might want to think of while studying binary neutron star mergers, and it's the dividing line between explosions, relativistic explosions that are associated with this compact binary mergers and those that arise from core collapse. So we've known since the discovery of gamma ray bursts that there are 2 families of those relativistic jets. One, we think, again, are associated like GW 170817 to binary neutron star mergers, but what we have usually tagged as long duration in terms of longer duration in gamma rays, GRBs have been thought to be related to the collapse of massive stars. So this division of progenitors versus type of light curve in gamma rays has been challenged recently by some gamma ray burst events. I'm citing here this 211211A. Regardless of the name, what it is a gamma ray burst that if you look at the light curves in gamma rays, much longer than what we've seen for GW 170817. So by all light curve duration and hardness duration parameters that we usually use to map GRB properties to progenitors, this would have been classified as what we call a long GRB, or a gamma ray burst presumably associated with a core collapse and not with a binary neutron star merger. But then some of the many papers that were published here, not making justice to the literature, it's hard to cite them all. But the astonishing part of this event was there was in fact a optical transient that resembled a kilonova rather than what you would expect like a supernova from a core collapse event. And so this has challenged our understanding of the dividing line between what's associated with a binary neutron star merger and what is a core collapse. And I'm highlighting this paper here from people in the room who've worked, in fact, on explaining potential different progenitor models for this event. But what I guess I'm trying to highlight here is linking those relativistic jets to progenitors will shed light on events like this that are really on the dividing line, and we aren't really able to classify them. Until we wait for more detections and things like improved gravitational wave detectors, however, I want to focus on what we can do on electromagnetic emission only. And so one interesting idea, at least that seemed solid in the past, is to distinguish this 2 type of gamma ray bursts of relativistic jets as being associated to supernovae or compact binary mergers by simply looking for an associated core collapse explosion after the event. And so those long duration GRBs or collapsar events are typically observed to be associated with stripped envelope core collapse supernovae that we called supernovae type C. And in their spectra, some examples are shown here. The ones that are seen to be observed associated with gamma ray bursts have broad lines, so they are indicative of high photospheric velocities. So you could argue, well, if we don't have gravitational waves, can we just distinguish the progenitors by saying, I call a collapsar gamma ray burst for which I see an associated supernova, and I call compact binary collisions at GRB for which I see a kilonova, just using electromagnetic emission. The challenge to that, it's very tempting to do that, but the challenge is really that there have been not just example of GRBs that looked like long and had a kilonova associated, but there have been example of GRBs that look like long, so core collapses, for which, like these two examples shown here, if you look in the optical at long enough times after the GRB, the supernova signature that is supposed to arise after the GRB itself has faded is lacking. It's not there to very deep limits. And so this is very puzzling, like where is the supernova that should be there? From a theoretical perspective, there's a whole variety of models. You could go from a failed supernova scenario where there should be no supernova accompanying a long GRB up to a collapsar scenario where all long GRBs should make supernovae. So there's a variety of possibilities. And what I've been thinking in recent years is what can we do observationally to distinguish them? So one interesting scenario is one in which you can have a continuity of events where a core collapse could give rise to what you would say almost symmetric ejecta just powering an ordinary optical supernova. Some of them, for some reason, we know only a rare fraction, also emit relativistic jets that power gamma ray bursts. So the question is, can we understand what goes on in terms of the link between relativistic jets and progenitors if we look at in-between events where you can have a supernova, but that supernova, it's not obviously associated with a GRB in gamma rays, but might be associated with a slower ejecta, perhaps again 30% the speed of light, which could be visible in the radio. Now, the reason why I'm bringing this up in the context of a multi-messenger talk is that there have been several models recently suggesting that part of this sort of core collapse event could also be sources of high energy neutrinos, and particularly there seems to be there might be a connection between those that aren't as bright in gamma rays and those that might be better sources of high energy neutrinos. So I'm quoting a few references over there. What we have been doing lately is taking a census of this core collapse Broadline 1c supernovae with the Zwicky transient facility. The reason why we're doing this now, and we haven't done that in the past, is that those events are relatively rare, so they're detected only now at a rate of 10 events per year or so, and there were 10 in a decade before, roughly speaking. So what you see here, again, observations in the radio. This is luminosity as a function of time since explosion. It's a very busy plot, but the feature I want you to focus on is that those supernovae that are associated with gamma ray bursts, so of the well-defined type that launch jets, are very bright typically in the radio, so they sit up here. And those that we call ordinary Broadline 1Cs that presumably do not make a jet, are sitting down here, so upper limits constraining them. So the question is what lies in between, and we've been populating this diagram, basically arriving to the conclusion that things like the prototypical supernova associated with long GRB, this is for those of you who are familiar, 1998 BW, are rather rare explosions, and so we've constrained them to be less than 19% of Broadline 1C explosions. But what is emerging from our radio observations, this is a little bit clearer plot, is that this in-between explosion where you could have, say, transrelativistic ejecta, perhaps associated with jets that are better efficient at producing high energy neutrinos, could be a more decent fraction of the total. This plot shows you as a function of radio luminosity and peak in the radio light curve, how you can constrain the speed of the ejecta. This is V equals C line. Those events here are superluminal because this is a non-relativistic approximation. And then you see 50% the speed of light, 30% the speed of light, and 10% the speed of light. And so these magenta dots are highlighting that we're starting to detect quite a bit of them in this in-between transition space between, say, 20, 30% the speed of light and relativistic events like GRBs. And so there are several projections that make interesting predictions of whether events like this sit in between ordinary gamma ray bursts and translativistic explosion could contribute to the high energy neutrino flux observed by IceCube. Here I'm just putting a plot from this recent paper, which is showing the IceCube measurements down here, and then various projections of what you could do if you keep increasing this sample of Broadline 1C supernovae. So you go from something like all of the supernovae that were detected in 2018 of this type, which are up here, up to what you could do in projection with a rate of 10 events per year over, say, the next few years that would drop this line really close to the neutrino data if we were sure that all of these events were making this transrelativistic explosion. The major factor of uncertainty is that the fraction of those making, say, 30% the speed of light ejecta is only constrained in a portion of the parameter space, not so much down there. So we're really still in the process of constraining this, but this should be a motivating scenario going forward. Okay, and I am at 11:50, so I'll conclude here. So conclusions and prospects, I would say, well, I hope I've highlighted that we're really into a scientific revolution, entered a scientific revolution with what we can do with gravitational waves and light together. But we really do need, I think, going from 1 to 10 in the next 5 years, or the field will greatly suffer, in my opinion. And so I really hope we get there. The open questions are a lot. GW 170817 has taught us a lot, but left more open questions. And I've highlighted them in terms of progenitors and outflows and mapping them from one to the other, including remnant properties. 04 is running, fingers crossed that we're going to have events with decent localizations. But the message I hope I also gave you is that in addition to being excited with the data that are coming down right now, now is really the time to start planning on what's next, or in 10 years we won't have you know, the facilities that would enable to really change the science we're doing today. So one is certainly, one concept is out there is certainly Cosmic Explorer, and I hope that national radio facilities in general, electromagnetic facilities, will proceed to map that sensitivity, increased sensitivity of gravitational waves. And I'll end here, and thank you for your attention.
Thank you for that very exciting talk. Are there questions?
As you follow up more broadline 1Cs in the radio, you'd expect at some point to see an off-axis afterglow. Is the lack of that surprising?
Yes, that's an excellent question. So not yet, because the upper limits that we have gotten so far are only constraining in terms of off-axis afterglow for the tip of the ISM density. And so if it is a wind ejecta, for example, or a lower density, we're not constraining. So the levels in which they are constraining is only to this, let me see if I can find it here, to that particular GRB up there. So not very much indeed. The key to doing that would be to be able to observe later, a later time, so several years time scales. And we had difficulties in convincing the time allocation committees of multi-year projects. I think there is a prospect for changing that if we get a steady flow of these events. The problem is these supernovae are so rare that, you know, when it's a few per year, why should you do a multi-year? But if it starts to be with Rubin, that we see several tens per year, and then we can say this could be a large program. So say 3 years on the VLA, I think that would constrain that portion. Yep.
Other questions? Are you surprised by the lack of detections so far in 04 for plausible candidates?
No, not yet. Not yet. So again, the rates, you know, we're still well within the run, and the rates are, you know, within. We have large uncertainties, but I think I'm definitely not surprised, because as we were chatting, Virgo is actually not joined yet, so it's delayed compared to the initial projection, and so these localizations area, it's a big word to call them localizations. They're kind of really huge. So there have been efforts going on for some of the events, but I am very much not surprised that we haven't found another GW 170817. I will be surprised, I would say, or at least you know, partially discouraged if we don't detect them by the end of 04. Now the rate again is the uncertainty is large enough that it could happen, but I am on the positive end of the spectrum here.
Other questions for Alessandra?
Yeah. So for Virgo, are you allowed to say, so last I heard, which was months ago, the major part of the time commitment there was pulling the vacuum again. Mm-hmm. Do you know what the status of
Yeah, there is some internal information that I don't think they want to, but yeah, so there's issues. And what I could say, I think, is that right now they're actually trying to get back to the O3 level of sensitivity. So that's what's very worrisome. I really hope that, you know, by the end of the year or early next year, we're going to reach that point. But I have to say, if Virgo does not join the O4 run, and so to a decent level of sensitivity, that's where I'm going to get towards the skeptical side that, you know, that we might not be able to find another of these events. Yeah.
Any other questions?
So there is a measurement of the Hubble constant using the jet structure of the binary neutron star. So do you think that that will improve in O4 or with your theories?
Yes, I think I have that type of measurement I think you're referring. So the idea is that, you know, for gravitational wave observations, you're kind of plagued by this degeneracy between the inclination angle and, you know, the distance to the event. And so in the case of GW 170817, the, you know, the contours, the constraints that of distance versus inclination that the GW observations alone have put as this yellow contour. And so for GW 170817 in the radio, what we were able to do is measure the proper, the superluminal motion. So the idea is you have this jet that is off axis. So here is to the Earth, that's the jet, and you're seeing it expanding. So what this would cause is a movement of the centroid of the radio emission on the sky, and you can measure from the superluminal constraints. You can put some additional, you know, independent constraint from the radio emission on the distance versus inclination, and overall that improves a lot the distance measurement. In turn, the distance measurements affects, you know, the H0 measurement. So this is all great. I think the short answer is, you know, unless we go to these tens of events, I think it's going to be hard to be competitive. With Cosmic Explorer, it will change a lot. So you'll get to the 1% constraint and so on. I have been discussing with several colleagues, you know, that are more interested in the cosmological, you know, independent measurements. And I think the real interest in the LIGO measurement is not so much on how precise they could get, but the fact that they offer a completely independent constraint. But I do think that, again, if we don't get to this 10-ish of events, it's going to be hard. Yeah.
I'm just curious on this point. So there's, you know, decent uncertainty in the exact angular structure of the jet.
Yes.
So does that introduce some systematic uncertainty in how one interprets the inclination angle here and hence in H0?
Yes. Well, yes, I do think so. Now, to what extent, I am not sure. We are conducting some simulations right now just because of that, especially not so much with the VLA, but for the next generation very large array. There are several papers that, for example, discuss the kilonova ejecta, like the fast ejecta tail, plus the jet, plus the structure of the jet. Would you really be able to infer something more than a centroid movement, basically? And I think that the answer is it's not going to be that easy. So I think that the centroid moving is always going to be a decent enough, you know, more direct measurement that something must be jetted at least, versus, you know, there were original claims of the cocoon emission so that it could lack a jet altogether. So I think a fair assessment is if you see something like this, there must be something that is a jet properly called and not just symmetric. Whether or not you can really go beyond just the centroid movement and seeing a structure there, I think the prospects for that without the NGVLA are really tough. You know, it's especially if the roll as dim as GW 170817. I do want to bring up that there's another way to do this, which could be polarization in the X-ray, in the radio signal. Because if something is off axis, then you should be able to see some degree of polarization from the non-axis symmetric view. We have tried that measurement for GW 170817, but the centroid movement won because we only got upper limits. It was so dim that, you know, to get to a few percent of 10% polarization, you really need a lot of flux. But I do see prospects in the future for having the polarization detection plus the centroid movement. Then I think it would really tell you something more.
So there have been like two NSBH detections, or triggers so far. Have there been any efforts to follow up in radio?
There has been no outstanding candidate association, none that we're following for sure. Yep. But you know, the localization areas, as I said, are very challenging. And then the ones that have too much of a mass ratio, so the total mass is too high, then it's not worth spending, you know, your trigger on it because it's likely not going to be bright in the radio. So we haven't personally triggered on anything yet. Yep. That would be a very interesting prospect of catching at least one black hole in NS. But I was talking today that maybe we should be putting upper limits for those. At least they might be of some interest. So I think we're going to end up that way towards the end of the run when we have all of observing time and we haven't used it, then we might spend a bunch on those.
All right, I suggest let's move the conversation now to the Bacall lunch. I was asked to remind you all that the Bacall lunch today is going to be in Rubin Commons, not Simon's Hall, so we can all just make our way over there again. And let's thank Alessandra once again.